Today, we're going to dive into one of the most incredible manufacturing processes on the planet, how we make a custom computer chip. Seriously, it's a journey that literally turns pure language into a physical silicon brain.
I mean, think about it. These things are everywhere, your phone, your car, your laptop, but how do they actually come to be? How does this simple idea evolve into the tiny, unbelievably powerful brain that runs pretty much our entire modern world? Well, it's this amazing process of translation. You start with just a description written in code of what a chip is supposed to do, and you end up with a microscopic, geometric blueprint detailing exactly how it's going to be built, layer by layer. Now, this whole thing is a super structured flow, right? It goes all the way from a high-level concept down to the actual factory production. Today, we're going to zoom in on the absolute heart of this process, turning that digital logic into a physical blueprint. It all starts with the language. So everything kicks off in the digital realm. Before you can even think about silicon or wires, you have to perfectly describe the chip's behavior using a special kind of code. This is what we call the front end of the design process. And we're talking specifically about ASICs here. That stands for Application Specific Integrated Circuit. So unlike the general-purpose CPU in your computer that can do a million different things, these chips are custom built for one single job. And that makes them ridiculously fast and efficient. The whole design process starts out pretty simple, kind of like this block diagram for a floating point multiplier. You just define what goes in, a clock signal, a reset, the two numbers you want to multiply, and what comes out, the answer, and maybe a few flags to say it's done. It's a very high-level, functional view. So you take that block diagram and you describe it in what's called RTL code. The best way to think about this is like an architect's functional plan for a building. It doesn't say what the walls are made of, but it spells out the purpose of every single room and how they all connect and work together. Okay, now for the really cool part. This is where the digital world smacks right into the physical one. We take that abstract behavioral description from the code, and we start what's called the back-end process, actually translating that code into a concrete manufacturable layout. I know this flowchart looks a little intense, but it's the essential mat for our journey. See, we start at the top with our RTL code. That code gets fed into a synthesis tool, which magically turns it into a schematic of logic gates. We call that a netlist. Then that netlist goes through place and route tools, which physically arrange those millions of gates. After a ton of checks, the final output is a file called GDSI. This entire flow, right here, is the core of modern chip design. So that first big step on our map is logical synthesis. This is where a super powerful piece of software reads our RTL code, our behavioral plan, and translates it into a gate-level netlist. You can think of this as the very first real schematic. It's a massive list of millions of tiny standard components, or logic gates, and a map of how every single one is connected. All right, so now we've got our huge schematic of logic gates. We're ready to tackle the three most critical stages of creating the physical layout: floor planning, placement, and routing. Honestly, the easiest way to wrap your head around this is to think of it like building a city from scratch. First, you have to zone the land and figure out where the big stuff goes, like the airport and power plants. Then, you place all the smaller buildings. And finally, you connect everything with roads. Floor planning is that zoning phase. We decide the chip's total area, where signals are going to come in and out, and we place the biggest components, like memory blocks. Getting this right is absolutely crucial. A bad floor plan can create these massive data traffic jams, making the chip slow or, well, just not work at all. Next up is placement. This is where an automated tool takes those millions of tiny logic gates from our netlist and precisely places them inside the floor plan. The whole goal here is to arrange them in a way that minimizes the distance signals have to travel. It's all about speed and performance. And finally, we get to routing. This is where we build all the roads. Another automated tool creates this unbelievably complex, multi-layered network of microscopic metal wires to connect every single component. This is the step that turns millions of separate little buildings into one single functioning city. This table really breaks it down nicely. You can see how the focus totally shifts. You go from the high-level architectural strategy of floor planning to the insane optimization puzzle of placement, and then finally to the incredibly complex, rule-driven job of routing, where you have to make sure millions of tiny wires don't short each other out. And here you go. Check out this transformation. On the left, you've got a little piece of the logical netlist. It's clean, it's organized, it's schematic. And on the right, That's the corresponding physical layout. It is a mind-bogglingly dense web of polygons and wires, all perfectly placed and connected by this automated process. So, after all of that complex digital construction, what are we left with? We have the final master plan, the blueprint that's ready for the factory.
This master plan is called a GDSI file. It's basically a giant database that holds the exact geometric coordinates for every single shape on every single layer of the chip. This is the digital file that a foundry, like TSMC, uses to actually build the physical silicon wafer.
You know, a huge goal of this whole backend process is just raw optimization. Look at this chart. It shows how the physical synthesis, the smart placement, and routing dramatically shrinks the chip's total area. And this isn't just about saving space. A smaller chip is cheaper to make, it uses less power, and it can run a heck of a lot faster.
So, after seeing this whole journey, from abstract code all the way to a physical blueprint, what's the big takeaway here?
The really crucial point is this. Chip design is a translation from language to geometry. The front end is all about defining behavior with code. The back end is about creating a physical reality with shapes. And that entire back end process, every single step, is governed by this constant, complex balancing act between three things: power, performance, and area. You can almost never improve one without making one of the others worse. So the next time you pick up your smartphone, just take a second to think about the miniature city that's buzzing away inside of it. A city with literally billions of components and connections, all meticulously planned and built through a journey just like the one we've talked about. It's a true marvel of modern engineering, for sure.